Sketch the graph of f of x equals x times e to the negative x by following the guidelines for curve sketching. First, we find the domain of this function. This function can be rewritten as f of x equals x over e to the x, where the denominator can never be 0, so the domain of this function is negative infinity to infinity. Next, we find any intercept. To find the y-intercept, we just simply evaluate this function at x equals 0. 0 over e to the 0 is 0 over 1, which is 0. So the y-intercept is 0, 0. It is also the x-intercept because it crosses the x-axis at x equals 0. Alternatively, we can set the whole function x over e to the x equals 0 to find the x-intercept, and we see that this only occurs when x equals 0. Next, we find any symmetry if possible. To find symmetry, we simply replace x with negative x in the function. The numerator is negative x and the denominator is e to the negative x. This is not the original function f of x, so the function is not even. And even if we factor out the negative, we will see that this is not the same as negative f of x, so the function is not odd. This function is neither even or odd. We then find any asymptote. This is not a rational function because the denominator is not a polynomial. So to find any asymptote, we would need to use the limit at infinity or infinite limit. We take the limit at x goes to infinity or negative infinity of x over e to the x. We see that this is infinity over infinity, so we can use the L'Hopital rule. This is the limit at x goes to infinity of 1 over e to the x, which we know that it is 0. So we have a horizontal asymptote at y equals 0. We also should evaluate the limit at x goes to negative infinity of f of x. As x goes to negative infinity, x goes to negative infinity, and e to the x go to e to a very large negative number, and this is 1 over a very large number, which is 0. So we have a very large number over a very small number, which is a very large number, negative. This is not a horizontal asymptote, but it helps us with the end behavior of the graph of the function f. We know that at x goes to infinity, the function stays close to 0, and when x goes to negative infinity, the function decreases without bound. To find any vertical asymptote, we would require that the denominator is 0, but in this case, the denominator is never 0. So we only found one horizontal asymptote, y equals 0. To find the interval where the function is increasing or decreasing, we would need to have the information about f prime of x, so we would differentiate the function f of x using either the product rule or the quotient rule. Using the quotient rule, we would square the denominator and the derivative in the numerator times the denominator minus, keep the numerator times the derivative of the denominator, and we factor out e to the x in the numerator to get e to the x times the quantity 1 minus x over e to the 2x, and this is 0 when x equals 1. So we found one critical point at x equals 1. This is a critical number. We will construct the sign chart for f prime to determine the interval where the function f is increasing or decreasing and any local max and local min, but we will do that in a minute after we find the second derivative to determine the interval where the function is concave up or concave down. The first derivative is e to the x times 1 minus x over e to the 2x or e to the x squared. We simplified it to e to the x times 1 minus x over e to the x times e to the x so that e to the x cancelled out, leaving us with 1 minus x over e to the x. It is much simpler if we find the second derivative using this expression. The second derivative, using the quotient rule, we square the denominator and we differentiate the numerator. The derivative of 1 minus x is 0 minus 1 times the denominator minus the numerator. 1 minus x times the derivative of the denominator is e to the x. Simplifying this, we have negative e to the x minus e to the x plus x times e to the x over e to the x squared, but this is minus 2e to the x plus x times e to the x over e to the x squared. We factor out e to the x in the numerator to get negative 2 plus x left inside over e to the x squared, and this simplifies to x minus 2 over e to the x. The second derivative is 0 when x equals 2. This is not a critical point, but it is a cut point. Now that we have the information for the first and the second derivative, we will construct the sign chart for both and combine them. The sign chart for f prime, the only critical number is x equals 1. We see that if we plug any number between negative infinity to 1, such as 0, into the first derivative, we will see that 1 minus 0 is positive, so the function is increasing. We then plug any number from 1 to infinity into the first derivative, such as 2. We see that 1 minus 2 is negative, so the function is decreasing on the interval 1 to infinity. We then test the sign for the second derivative. We found the cut point at x equals 2. If we plug any number from negative infinity to 2, we will see that negative 5, for example, minus 2 is negative. So the function is concave down from negative infinity to positive 2. And we plug in any number from 2 to infinity, 5 for instance, we will see that f double prime is positive, so the function is concave up. We see that the function f has a local maximum at x equals 1 because f prime changes the sign from positive to negative, and it has an inflection point at x equals 2 because f double prime changes the sign at x equals 2. We then combine these cut points to form the combined side chart. We see that from negative infinity to 1, the function f is increasing and concave down. From 1 to 2, the function is decreasing and concave down. And from 2 to infinity, the function is decreasing and concave up. Decreasing, but still concave up. Keep in mind that we found the x-intercept to be x equals 0, y equals 0, which is also the y-intercept. If we plug in 1 to find the local maximum, we have 1 over e to the 1, which is 1 over e. If we plug in 2 to find the inflection point, we will have 2 over e squared. We then combined these cut points in the xy axis. Remember that the first cut point is 1, not 0. At x equals 0, y equals 0. At x equals 1, y is 1 over e. And when x equals 2, y is 2 over e squared. The graph has to go through these points. From negative infinity to 1, the function is increasing and concave down, and it has to go through the x and y intercept and the maximum value. From 1 to 2, the function is decreasing and concave down, and it has to go through the maximum and the inflection point. From 2 to infinity, the function is decreasing and concave up, and it has to stay close to the horizontal asymptote y equals 0. So after 2, the function is decreasing and concave up, but it will never hit 0 or go back up again.